This is a Snap-on automotive diagnostic scan tool, and the battery pack has died in it. Availability of packs are a little hard to come by at the moment. There's no real rep for Snap-on in the country at the moment, so what we're going to do is see if we can resurrect it. Now, I already know that I've looked at this once before. Unfortunately, the battery management chip in here has given up. It's detected a problem and locked out the pack, and I have tried and looked everywhere, and no one seems to have a solution for being able to unlock that when it happens. The same as a laptop. Same chip is used in millions of laptops. Yeah, that's just one of those things. Unless you get the programming device from Texas Instruments and go through a whole process, and even then I don't know if it would even work, whether if the manufacturer has set any specific flags or bits that secret to them, that means that if you don't set those it won't work either. So she's a goner. So yeah, we'll have a look at what we can do to maybe rebuild that and make it work a little differently. Now, I might be completely wrong about how I'm going about this, but it could be an interesting little exercise anyway. Might even learn something. So my theory at the moment, I've got some brand new cells. They're all 18650 cells, and I have a little battery management circuit. There seem to be plenty of them about. It's quite a common one that people use for other projects. It will stop over voltage, over current, under voltage, all the important stuff. And I have fully tested it. I've charged the pack up, and it does cut out once the cells reach 4.2, a total of 12.4 volts. Or just above, there's a cutoff point, and it disconnects the pack from the input cable. I have fully discharged the pack, and yes, the cells all have full capacity as measured. Yeah, fully discharged, and it disconnected the pack once it got down to about 7.5 volts, which is 2.5 per cell, I think. So it's 4, 5, 2, 4, 6, 7.5. Yeah, it's 2.5 per cell, which the data sheet even says no less than 2.5. So that circuit is doing the business. The problem I see at the moment is these can't be charged any faster than 1.3 amps constant current as per the data sheet, and when they're dead flat, we're looking at about 10 volts. At 10 volts input, it's pulling that much. So our tablet is 19 volts in, like most laptops. And I just measured on the battery terminals in the tablet where the battery connects. I've measured 15.5, give or take, with no battery connected. So because it charges these, it's got a built-in system for charging these, of course, then it may self-regulate. We may not have to do anything other than hook it up as I've got it now, and because it's got the monitoring, so if there's a problem with any pair of cells, we'll be right. Can't imagine there'll be a problem for a few good 500 cycles or more, maybe plenty more. These are good. Capacity drop, what, 2.9 amp hour new, and I think the data sheet said it went down to about 2.2 or something after 500 cycles, so that's alright. Could take a while to get there. So yeah, so since these things, laptops and tablet whatnot, have all the charge controller built in, I'm wondering if maybe if we just hook it up as is, and that 15 volts may drop down and it may self-regulate and not charge it at a ridiculously screaming speed. Now the other thing that could happen is it may not charge at all. That the voltage we're measuring on the open terminals may completely disappear because there's definitely a communication line to these for gas gauge information and other stuff such as packers locked out, do not use, and or do not charge. It may, so the motherboard may need to see a specific bit in the communication stream that says OK charge. So that may not work at all. We may need a external charge source, and if that's the case, we're going to need yet another little board, maybe something like that, which is a very common adjustable voltage regulator. Takes a wide input range and spits out a wide output. Only this one's not a constant current version, and so we'll need something like that. Well, I don't have one, but they're easy enough to get. And incorporate it all back into the case, or a slightly modified version thereof. So let's have a look at the tablet and see if that 15 volt output is anyway regulated, and I think what we'll do is pop our load onto it and very gently wind up the current draw from it. But first of all, we're going to need to know which pins are positive and negative, because I've actually got I believe that's ground, and then it goes 12, 12, or 12, nothing, 12, 12, 15. So we need to, I think it's the two outer pins usually, but just in case it's the two beside each other, we'll have a look at this bit of PCB that's in here, figure that out, and then see what happens. So with the board out now, I don't know what voltage these are at the moment anyway. The fuses that they use in these packs are really interesting. They've got quite often they're a 3-pin fuse like this one, and what happens is, here we got 3.9 volts. What have we got there? 2.9, 1.5, nothing, or half. So yeah, these cells are done for. But anyway, yeah, the fuse is in these 3-wire fuse, and what can happen is, if the management IC detects there's a problem with say a pair of cells, what it will do is it can actually blow the fuse. It's got a little, well, a low resistance, effectively like a heating element, in the fuse, and all it has to do is switch on a transistor, which passes a current through that part of the fuse and destroys the fuse itself. So yeah, I mean, all in the name of safety, of course. You understand why they do these things. So which pins are our main feed? Yep, there we go. So we've got on the very end, it says P+, that's going to be a positive. We've got C, D, TH is thermal, so that's our temperature. ID, so that's going to be something that the system uses to identify what's attached. And then P minus. So it's definitely the two outer ones, and if this was working, which it isn't, I'm just going to probe it anyway. What have we got there? Yeah, nothing. So we have the connector down in here, and it says plugged in at the moment. And if we probe across the two outer ones in the right mode. Okay, we've got 15 volts there, just idling away. Oh, get a better connection. Yeah, 15 volts idling away there, so be interesting to see what happens to that when we pop a little bit of a load on it. Okay, so if we hook up our load, ooh, it's not even set to on and it dropped right down. Interesting. I guess that is not a high current source in its current state of operation. We try that again. Yeah, it drops up, yeah, it drops back down. Oh, that's no good. Okay, so where are we at with this? Well, this works. I did some testing using my electronic load, that thing there that we have reviewed before. It works really well for all the basic stuff. So I pulled the let it drain it completely down, and I think 2.5 volts per cell is what the data sheet says is completely flat. So we went down to that. It pulled just under 6 amp hours, which is expected with 2 lots in parallel. So that's really good. Now I've given it a partial charge because you shouldn't let them sit discharged for too long. What I did find was when I discharged it, it got down to below, interestingly enough, this is configured about 2.5 volts, so it got down below 2.5 volts per cell, and this board disconnected the load from the pack, so good protection there. And when fully charged, we, well, I don't think I filmed that bit, but it saw that this board disconnects the load from the power supply at full charge. Excellent. Now we can't use the tablet to charge that anymore, so what I have now is, voila, a little device that I mentioned and now have. So this is a simple buck regulator. We have that pot, you can adjust the maximum voltage, and this pot allows you to adjust the maximum current. And the regulator there, which is a LM2598S, which is used in a lot of little boards like this, has a feedback pin, but a little bit of trickery. They add a couple of parts in this pot, and you can have an adjustable constant current source, so that's really handy. We're going to test this. We're going to let this charge the pack up, and I'm going to charge it at 1 amp. We'll see how hot it gets. I really don't want to have to connect this to a heat sink, because I've got to find out where it's going to sit, if it's going to somehow incorporate it with the pack itself, in which case, if I need to adjust the profile, I could take these multi-turn pots off and put a fixed resistor in there for what I need it for. So anyway, we'll monitor the temperature at 1 amp. If we have to, I suppose we could go to 800 milliamps. I don't want to do a half amp charge, because in a pack this size it'll just take forever. It's bad enough on a tablet, so with a good amp hour pack on it. And I'm going to do it at 19 volts in, because that's the voltage for the charger that runs this thing. Same as a laptop, it's kind of designed around a laptop similarly. Anyway, so yeah, so we'll see how this performs and how hot it gets, and then we'll make a call as to how we're going to set this up. And I'm thinking, if there's enough room, I think there is a bit of room in the case, I might mount this inside the case of the tablet, hook it up internally. There's a DC jack on the side of the tablet, and if I have that hooked to the DC jack, then that can charge the pack and run the tablet at the same time. Where are we going? Positive. Positive's on top. Negative. Need to make this blue one more flexible. It's quite a stiff fly lead there, so that it tends to want to pull everything around with it. So we are, everything's hooked up, and our output is set. Where's a thermocouple? Might just tape that to the back of the board, perhaps. That might be better. That's a dirty bit of tape. Should be right. Right. Plug her in, turn her on. We have a red light, which means it is in constant current mode, and when it goes blue light, that means it's very little current being drawn. Constant voltage mode. Now I've got my temperature probe, and that's sitting there quite happily climbing up. It'll be really interesting to see what this actually gets up to about. And I will stick a probe on the battery just to check the voltage there. So if we watch it for long enough, we will actually see that the pack voltage is climbing, which proves that it is taking a charge. Here we go. It's crept up another one to 11.83. Let's, out of curiosity, we'll just put an ammeter on that. Ah, that is only 895. So that is tunable a little bit more. Where's my screwdriver? So at 900 milliamps, I might just leave it on 900 milliamps though. It's climbing up to about, well, it's 50 degrees Celsius already. So probably a bit hot. And that's dropping 19 volts to, I'm picking, well, 11, 12, 11, whatever it is, about 11.8. Interesting on that temperature. If I stick my finger on it, it doesn't actually feel like 50. I'm sure I can trust this extremely cheap temperature probe. Right on the limit of the datasheet that says to stick a heatsink on it if you're going to run it at greater than 10 watts, and we're running about 9.5 watts. So yeah, in an enclosed space too, it will make a bit of a difference. Well, that seems to have plateaued. It's not really getting any hotter, so that's with no heatsink and an ambient temperature of about 22 in the room, I think. 20, 22, yeah. So we've got a total of about 5.8 amp hour, 2.9 amp hour cells. In parallel, we've got about that much. And at 900 milliamp charge rate, it's going to take about 6 hours for a fully flat pack. So yeah, this could be here a while. I might just now we know it's doing the business, I'm probably going to fast charge it off my bench supply directly, and toward the end I'll pop this this little regulator back on and make sure that it finishes the charge cycle and all works happily with the protection board. A little tricky to really catch because of how slow it charges toward the end of it, but yes, it is working as it needs to. The management board has a cutoff of about 4.3 volts overcharge protection, so I mean you only should charge it to 4.2, but there's got to be some leeway in there somewhere, I guess, otherwise they would have made it 4.2, since most cells I think rated that, but anyway, it dropped down to quite a low current threshold with the output voltage that I had set was about 12.8, and it was down to about 90 milliamps, and it still had quite a long way to go to get to the cutoff voltage. So I just tweaked up the voltage pot so that it was pushing about 100 milliamps right to the end, and I think that's going to be the best way to do it. Time will tell, but let's see how we can mount all this in a nice tidy fashion. This is temporary, I'm going to put some thicker wire in there. That wire is not really designed for an amp or two, and I don't think it's going to pull a couple amps, but well, who knows. And yeah, we'll see what we can do about mounting the charger and hook it all up, and hopefully get a nice tidy solution. Well, it's actually been a few weeks since I started this, since the last section that you just saw before the cut to the scene, and I got pretty busy with stuff as well, but also in the back of my mind I just couldn't stop thinking that there has to be an easier, well, not easier, a more discrete, or what's the word I'm looking for, a more integrated, a better solution, a better way to do this. So I spent a lot of time going over the motherboard and reverse engineered the input, the battery slash DC in circuitry, and understanding how that switches between the two and what controls the charging, because this is already set up to charge. This has a charge controller and everything built in, so why can't we use the one that's on the board? And I have figured it out, and I will show you what that relates to. But at the moment I've started getting this all back together. I've still kept the battery management board. We're not going to need this because we're going to use the motherboard to charge it. So I've kept that for protection in case, you know, something goes wrong or the pack is drained very low. Yeah, and I've just retained the original board from the battery pack. I've wiped all of the parts off it. There's nothing on here except for one resistor, basically, and I'll show you why in a moment. But yeah, I've kept that, so we've got the interface to the motherboard. We've got the connector still there, and it's just easier to leave it on the board and connect to that. A little bit of work to do here because it doesn't go back together perfectly. This doesn't fit exactly. This has got little sections here that I've broken off these ones thinking it might sit up against the board, but it's still a bit large, so I may have to put a window in the case to allow that to sit down and then just seal up. It may stick out just ever so slightly, but we'll look at that in a moment. It actually goes on that way, but we do need to put that back on. So let's go over what I did with the motherboard. Okay, so this is the setup. Feel free to criticize my ability to draw schematics. I do not do it very often. Now, quick explanation. Can I turn the grid on and off? Grid settings, views, a grid on, oh, show grid. Okay, that's better. Okay, I've added 3 MOSFETs and 5 resistors, and this is how it works, and I'll go over it on the motherboard as well, but just to give you the gist of it, from the battery there's one of the pins I have isolated from the motherboard from the rest of the circuit and used it for a input signal as a battery is present signal. Now that's coming via a 1k ohm resistor, so it's just it's not able to give a lot of current, but that comes along here, and when the battery is present, that signal turns on this MOSFET, which goes off to the input FET. So the input FET is used to switch between battery or DC in as a source. So normally what would happen is the BIOS would communicate with the battery management chip and say, hey, what's going on? Are you okay? Can I use you? Or are we charging or what? But that's not going to happen anymore. And without this intervention, see, the BIOS doesn't turn on the input FET and allow the battery voltage to go through to the rest of the system. So we have to force it to turn on ourselves. So that's what this one does. And there's a resistor there just to limit the current to ground, because this is switching directly to ground. The input FET is a P-channel FET, and it must be pulled, the gate must be pulled to ground to turn that on. Now what happens when you plug in the charger? Well, we don't want to leave that FET in battery position, so up the top left here we have from DC input. When the DC input or charger is connected, it turns on this MOSFET, which pulls this battery input signal to ground, which turns off this MOSFET, and that causes the input FET to go back to its original state and allow it to run off the charger. These resistors are purely for current limiting or to maintain an off state. So we've got this one here maintains this FET in an off state when the battery is disconnected, just so it doesn't float. If you leave it floating, it'll just flick off and on, or turn on and stay on and give undesired effects. So this resistor up the top here is used to ground, just to keep this MOSFET in an off state as well when the DC charger is not attached. So yeah, then here's the other half that we get to make the charging circuit operate, because the operating system and or BIOS control, probably just the BIOS really, to be honest. I don't think the OS would really intervene with battery charging. It'll show the percentage of battery life, but I don't know if it controls charging. You'd think it would be a hardware level, possibly in the BIOS, but who knows. But anyway, this IC symbol in the top right here is the closest. It's just a basic charge controller chip. The actual controller chip is this. It's a what's the number? LT4012. It's probably right in front of me. LTC4012 charge control IC, and at the bottom of the data sheet we have this application sample application schematic, which is pretty much how it's set up in this case. And there's our input FET. There's up at the top middle there, Q5. That's our input FET, which we are controlling and over here on the very right there is a Zener diode and another MOSFET which is used as well. But I mean, it wasn't quite hooked up the same as it's drawn here. It's very, very similar, but not quite, because the battery does come through the MOSFET on the right here, which is turned off when we get our DC in connected. But once it goes through this MOSFET, as I'll show you on the board itself, the one in the middle here, which is our in FET they call it, but yeah, that FET there seemed to be on the other side of this line, because you would think, yeah, okay, this would power, says to power to system, so when this is switched on, the battery voltage, here's our battery down the bottom here, that would flow straight up and out, through the MOSFET and out to the system, but it doesn't. It actually ends up going to this FET and then off to the system, so it wasn't quite that simple. But anyway, for this IC to start charging, it needs to get an enable signal, and the enable signal is 0 to supply voltage, which in this case is 7, I think, is the maximum that this chip runs on. But anyway, so there's a 3 volt line there. So here we've got up the top plus 3 volts, pull up to enable. So what happens there is we don't want this, because of the way that I've got it set up now. If I were to leave that enable connected to plus 3 volts so that the chip would run, when the battery was connected without the charger, charger plugged in, the DC input, then this would still be active and trying to charge the battery off of the battery, and that's not really good. I don't know, in practice what would really happen there. It might just drain the battery a little faster, it might achieve nothing, I don't know. But I want it to be a bit more thorough than that. So here we have this FET, and what happens is when the battery is connected without the charger, this from battery signal not only turns on this FET, but it also turns on this FET, which pulls this 3 volt to ground. So through the resistor, of course. Have I drawn that right? I don't know if I've drawn that right. No, I have drawn that right. No, I have not drawn that right. Okay, sorry. What it should look like is something more like this. That's better. So let's just link those two back up, and that can go to there. That's better. Right, that makes more sense. Yeah, so trust me, this is how it is in practice. I just drew it wrong before I started the video. So once that switches on, it pulls the signal here to ground. It's through 100 ohms, so it's only a few milliamps, so it's not overloading our supply, our 3 volt main 3 volt line there, and that keeps that chip from turning on. So then, oh, where are we? When the DC input comes in, turns on this FET, it pulls this signal to ground as well, which turns off. It's the same signal, so this turns off and this turns off, and because that's off, we get enable, and the chip fires up and starts charging the pack. Make sense? Any questions? Yeah, it's fairly straightforward. I really should have not procrastinated on it, but it's a lot simpler than it than it looked originally. Okay, let's go under the microscope and I will cover it, how it actually sits practically. Right, what we're looking at here, this is our input FET. So this switches depending on whether we are running off DC input or battery. And this is a dual FET package that switches this inductor here for charging the battery. So this is a charging circuit. Down here in this empty section on the opposite side is our battery charge control IC. So there's a signal that comes up from that to this FET and this FET as well, but we are overriding that at the moment. This wire here is going to the gate, and that is going to the first MOSFET that I pointed out on the schematic that I drew. This just a bit further down here is another MOSFET. That's the one on the very top right of the application schematic for the charging IC from the data sheet, and that FET, and this is a Zener diode here which is off the gate, so when the voltage here is high enough it breaks through, and because it's a 19 volts charger, so we've got 12 volt battery, but 19 volts overcomes the Zener and trips the gate on that. So that's how that works. Yeah, so not much to see on that side, but that's that part. And then I'll flip it over. On the top there, this is where the wire comes from that FET. I've just run it along here, and I'm going to glue things down into place once I've done this, but for the meantime, that's the bit of a jumble that I've got. Yeah. Here is the line from that FET. This is the current limiting resistor. Here is that FET, the first FET there, which is you controlling that. Now, I really wanted another SOT23 package, but it was hard enough finding this one here, this is our charge enable FET. But yeah, I ended up using this larger package here as the DC in control FET. Yeah, I'm sure it could be done tidier, but as I said, I'm going to hot snot that into place, and it will sit there forever and a day and be just fine. This resistor here, this one here, that's going to the gate of the DC in FET there, just to hold that to ground, as is this resistor, which sits neatly between the legs of the SOT23 package. That's pulling this to ground when it's inactive. We've got a wire link over here to the drain, and this wire here is going to the gate of our charge control FET, with the source going to ground. The charge control FET is also connected to ground. I just ran over to that surface mount capacitor there, and then if we follow that wire comes along, and there is our charge control IC. And this was the original resistor here, so there was nothing here, and it just went from the enable pin through this resistor into the board somewhere. I'm guessing off to the BIOS or whatever will enable that. I've got that out the way. There's our current limiting resistor, pull up to 3 volts, so through here is our 3 volt circuit, comes from our 3 volt supply, so I've got that just directly across, and then because this comes down to here, I'm using that as our point of attachment to connect to the FET there. So that's how that works. And I mean, yeah, it took a little while to figure it out. I kept getting distracted, of course, but just reading data sheets and finding out what goes where. There's a lot of measurements that needed to be taken. For example, it's a bit hard to tell under a microscope, but I could probably show it on the camera. So here is a better view of the overall board. Down here, the bottom, that's our input FET that I showed up close. The problem I was getting was I had voltage around here, battery voltage around here, but it was getting stuck somewhere and I couldn't figure it out, because over here, this capacitor here was had nothing on it, yet when the DC in was connected, it had voltage, actually had 12 volts. There seems to be this IC here is operating these FETs and switching across this large inductor to drop 19 to 12, and it's feeding the rest of the circuit that way. And you know, after a lot of measurements, I found that it all sort of revolved around this FET. And then I took my chance and I did an experiment and I controlled the gate of that, and sure as eggs, once I did that, we had battery voltage appearing where I needed it, so over here. So yeah, and there's where everything sits, and up the top there, my little work over here by the battery connector. So it works, it really does work, and it does switch off. It switches fast enough so when you pull off the DC in, it goes straight onto battery power, and when you plug in, it runs straight off the DC in. There's no, and under load, I made sure it was, you know, Windows booted and so forth, and it was quite happy. So now we just have to put it all together and make it presentable. I forgot to show where the DC in comes from. So here, this comes through a diode when you plug in the charger. This particular part is actually the dock, the cradle that the whole unit sits in. There's another DC in section for a jack on the side of the machine, but ultimately on this side of the diode, it's both are joined together. That just isolates the two, so I guess you can't put it on dock and plug in at the same time and expect cool things to happen. But I've just run a wire around here, avoiding the battery hole. No, sorry, that's a that goes somewhere else, that hole. Avoiding the hole cut out there, just run it up and around, and that's what goes over to a little jumble of fun. And there it is, booting up off its battery. And I'm going to run it and just see how long it runs for. We should get a good couple of hours out of it, I would have thought. Whatever the original pack life was, it will be the same. Basically, it's the same, if not better, individual cells that I've got. Panasonic, genuine Panasonic, I think they're 2.7 amp hour cells. And yep, look, no charger cable attached. Here's the charger cable. I promise. It's not sitting in its dock either. It's just on the bench. So we need to run the pack down, give it a cycle, make sure it's completely happy. Unfortunately, we've lost the ability to know what level of charge it's at. I guess you could bodge in some kind of indicator. I mean, there's the LED at the top, which used to turn red when charging. Maybe there'd be a way to incorporate something that uses that LED to show when it's low charge, maybe. I don't know. But Windows certainly isn't complaining that it can't read battery status, so that's the main thing. Well, I hope you like that. It's something a bit different, and maybe we'll do more of these mods as I find situations that require them. If you've got any thoughts on the matter, maybe you've done something similar, maybe you're well versed in building battery management systems, maybe you could let me know if it's going to fail completely in a week or so. I don't think it is. I think it'll be just fine, so long as its built-in charging system functions as it should. But yeah, we've got that over voltage, under voltage protection board on the pack as well, so we should be good to go. Thanks for watching.